Okay, so welcome to the faculty development program on eSIM on VLSI design using eSIM and OpenPDKs. And this is the second day, and we have an extra session, a special session. So today we have our guest as Steve Hoover, Mr. Steve Hoover, and he will be speaking on digital circuit simulation using eSIM and Makerchip, mostly about Makerchip. And he is the founder of Redwood EDA, and he's from USA, and he was former logic design lead at Intel. So he has a lot of things to speak about. He has developed a Makerchip EDA tool. It's an online IDE, and he is also developing and driving force behind the transaction level Verilog. So we have seen Verilog, we have seen system Verilog from emerging from Verilog, and then now a new language called as transaction level Verilog. So hope it will be a very much enriching session. So over to you, Steve.
Great. Everybody hear me well? So title's very simple. This talk is all about Makerchip, and we'll talk about how it's useful in the classroom. We'll end with how it integrates with eSIM, but mostly I'll be talking specifically about the Makerchip platform and various ways that you can use it. I'll start off with a demonstration of the platform. We'll talk about how to use it for AI-assisted learning using a VS Code extension. This is a work in progress extension, so it's not public yet, but this gives you a preview of things to come. And I'll talk about various options for how you might use these tools in your curriculum. I'll talk about transaction level Verilog, as Sumanto mentioned. My background is circuit design. That background gave me a lot of experience with the way things work and the way things don't work so well. And so about 11 years ago, I walked out the door from Intel to improve the situation for circuit designers and to introduce new design methodology and better tools. Verilog wouldn't cut it. There are a lot of legacy issues with Verilog. It stems from the 1985 timeframe. It was designed in a world where we worked with thousands of transistors, not billions, and the problems are very different. So to introduce better design methodology, I had to introduce new language. So it's really focused on high-end problems. At the same time, since I had to crack open Verilog, that gave me an opportunity to clean house a bit with the language. And so what we end up with is a cleaner language for circuit design, which means a language that's much more approachable for students than Verilog. And so we'll talk a bit about that. I'm not, this is not meant to be a presentation on TL Verilog and the modeling methodology and all of that. It's more about the platform, about Makerchip. But I will kind of illustrate some of the benefits of TL Verilog without going deeply into the language itself. And then we'll end with the eSIM team maybe presenting something, I'm not sure, or at least talking about the integration of eSIM and Makerchip. Kind of the state of that right now. We're in a transition, so I'm not sure demonstration is possible for everything, but through that transition, some good things are coming with the integration of Makerchip with eSIM. So that's the end of my slide deck. The rest of this is going to be, just demonstration. I do have other slides here. Maybe if there's extra time, we'll turn back to some of those. But I expect primarily, I'm just going to be using Makerchip and showing you all about it. So before, well, actually, before I jump into the technical content, I want to thank everybody for coming in the evening. I know you've had a full day and a day yesterday of presentations. It can get to be a lot, and I appreciate your time. Let me ask all of you just to get a better sense of who I'm talking with, and that will help me focus my attention on things that matter to you guys. So we have in the meet the reaction. Hopefully everybody knows where the reaction is. I'm just going to use that to take a quick poll, or you can just answer in the chat. But I want to get a sense of what you guys teach, so what your needs are, So let me first ask, how many of you or who of you uses FPGAs in your classroom or teaches about FPGAs? So yeah, just go ahead and click on the reaction button. Perfect. Many of you, that's great. Boom, awesome. How many of you teach an introduction to digital logic? Excellent. I'm talking to the right people. That's good to know. Perfect. How many of you teach computer organization? So CPU design, either uh, with Verilog or just textbook learning. Um, so computer organization, CPU design, RISC-V, all that good stuff. Show of thumbs. Not too many, actually. I'm surprised. RISC-V is supposed to be huge in India, right?
Yeah, RISC-V is growing in India actually. I want to add one thing. So Steve actually, I forgot to say that Steve actually helped us to integrate Validator and Makerchip with eSim. So thanks to Steve for that initiative and bringing out mixed signal simulation in eSim. Yeah,
Yeah, it's good to be in the platform.
he's associated with us since like last 5 years. Yeah, around 5 years. And we had a marathon also, which I described earlier.
Ah, good. Yeah, the marathon was fun.
Yeah.
Um, so one last question, who uses Verilog in their classes? Great. All right. So, truth be told, I have a harder time teaching TL Verilog to folks who know Verilog. It's easier for me to start from scratch from, teaching people that have no experience with Verilog whatsoever, even no experience with digital logic. I find that Verilog kind of honestly corrupts the thought process. But anyway, let's jump into Makerchip. So, do I have it open? Let me open a new session here. And we'll just poke around the platform a bit. So this is Makerchip. It has many of the things that you would expect of a circuit design IDE. So you've got a pane for editing your code. We're looking at TL Verilog, so the syntax here won't mean a whole lot to you. But this is just a starting TL Verilog template. We've got a logic diagram generated from your circuit. So let me open up something that's a little more interesting than just a logic reset. So we've got learning resources here, tutorials, examples, courses, documentation, and some papers. I'm just going to open up the examples page and find something to open up. So I think I've got a divide example here that will work. So here's a division circuit. So we have a logic diagram generated from our design. Of course, this is circuit design, so we have a waveform viewer. We can organize our layout. My goal in life is to make sure you spend as little time as possible in the waveform viewer. I remember when I left school and entered industry, my education kind of worked out where I didn't get any real hands-on experience with circuit design tools. So I walked in the door at Digital Equipment Corporation for my first job, and I said, okay, how do I do my job? How does this process work? How do we design circuits? And they pulled up a waveform viewer and they said, this is how you understand what's going on in the design. And I said, oh my God, you look at all that sea of mess and there's nothing to organize your thinking about this very complex thing. So I guess kind of from that experience, it's been my mission to make sure we design better than using a waveform viewer and just a sea of unorganized information. And I'll give you some exposure to what I'm talking about as we go through. So you get the diagram in the waveform viewer. We can click this button to go live and see the actual values. We can play the circuit forward or scroll manually to see how the values change in time. If we're debugging, maybe we've made our way to the waveform viewer and this 96 value doesn't look right. We can bring time to that cycle. We can highlight that signal. Here it is. We can step the simulation and see how that value moves through the circuit. Of course, we have a log. So the top here is a tool called Sandpiper, which is my tool, which is processing the transaction level Verilog into Verilog. And maybe it would help to bring up a picture of that. So this is a kind of an overview of how the platform works. You've got your editor where you're entering your code. You compile, and that gets sent to the cloud, to Makerchip server. It goes through some text pre-processing and then through Sandpiper, which, as I said, produces Verilog, or system Verilog. It also produces a bunch of collateral that we see. So it produces the data that becomes the diagram. It produces a few other things that I'll show in a second. That Verilog gets run through Verilator for simulation, compilation and simulation. And Verilator is producing a C++ simulator. So we're using G++ to run that simulation. That produces the trace file, which we view in the waveform viewer. And of course, all of these contribute to the logs. So that's what's happening behind the scenes. So one other thing, well, two other, yeah, is there a question?
Yeah. How transaction level Verilog or TLV is a little different from the normal Verilog? If you can compare a little bit and demonstrate, it will be much easier to understand.
Yeah, so I'll give you a quick high-level answer now, and I'll go through examples that kind of paint the big picture, right? Like I said, this talk isn't meant to be a deep dive on TL Verilog itself. If we have extra time, I can go deeper. But I want to start with kind of presenting what you can do with the tools, and then we can save deep dive for if we have time or another time, but we'll see. But the big picture of transaction level Verilog versus other technologies is, if we kind of scan the landscape of what folks are doing with hardware description languages right now. We've got the legacy languages, Verilog and VHDL primarily, RTL languages. You're all familiar with that. What's on the horizon, right? High-level synthesis has been a push. I don't know how old high-level synthesis is now, but it's been a thing for a long, long time. It hasn't really caught on the way people were hoping. It's based on, so the general idea there is to elevate the abstraction level so that you're writing hardware more like you would write a program, which most people view as being a simpler task. And you have tools that do amazing transformations on the logic that you've expressed to turn that into a circuit. It's nice to have that ideal that you just are able to write software and you push a button and it becomes hardware. Doesn't work all that great in practice. One of the main limiters there is that the technology has evolved around C++. C++ is not a hardware language. It had, it did not have hardware in mind at all when it came about. It provides a foundation for System C, which uses it to model hardware. But there are kind of legacy baggage associated with the C++ heritage of high-level synthesis. And then there's just the fact that the concept was a little bit eager. But there are, very powerful capabilities in high-level synthesis. I'm not I don't mean just to put down high-level synthesis. It's a very powerful set of capabilities. I decided to layer my new methodology on top of RTL because I didn't want to inherit some of the baggage that's inherent in the high-level synthesis tools. And it's a broader accepted technology. You also have a kind of the baggage of the goal of debugging with high-level synthesis is to leverage the C++ ecosystem. So you're using GCC as a hardware debugger, which is a very awkward prospect. In contrast to high-level synthesis, you have a community mainly driven by academia, which is focused on kind of fixing the language limitations of Verilog and VHDL. So you have a whole bunch of languages that attempt to leverage the benefits of modern software languages with a lot of capabilities that just don't exist in RTL languages. So any software language you can think of, there's a hardware description language that's built somehow on top of that language. My feeling is hardware is a unique enough thing that it deserves a language that is built specifically for hardware. So TL Verilog encapsulates some mechanisms of abstraction that are targeted at hardware and make sense for hardware. And you do have a couple languages, some of the more recent languages that are kind of inspired by software languages, but not directly leveraging them. So leveraging some of the ideas and the syntax. So that's kind of the landscape right now. I feel that TL Verilog is in a very unique position, that it was driven by my experience and the experience of my colleagues from decades in industry, concepts that have evolved. We've had a lot of, we meaning industry has had a lot of kind of point solutions to various limitations of RTL and the tooling. And so there were a couple realizations that kind of inspired me to walk out the door. I think primarily it was just getting to the point where I had enough money in the bank to do something stupid. But the kind of realizations were that if you put all of these point solutions to various problems together and kind of do a redesign, a clean redesign, there's a lot of synergy opportunities to really change the methodology dramatically. And so that's the end goal. Since I've left, so I started this technology within Intel. What was it? 2005 was probably kind of the genesis of my involvement in some of these concepts. And then since I've left Intel, the focus has been much less on the language than the ecosystem around it, and the tooling and Makerchip and all that. But yeah, so it was the realization that there's a lot of synergy in these concepts, and the realization that the industry's kind of had this dream that you could do design top down. You start with an abstract idea, you start with an instruction set architecture, and you model that, and then you refine that down and refine it until you get hardware. And if you had asked me 15 years ago if that was a feasible design methodology, I would have said no way. It's it's a pipe dream. It's as much a pipe dream as high level synthesis. The realization was it is tractable. It is a solvable problem. It's a hard problem. There's a lot that needs to be in place to enable it, but we really can do design top down. We can start from an ISA. We can refine that down and come up with hardware. But so sorry, that's somewhat of a long-winded answer that really doesn't answer the question, because I didn't talk about the language at all. But that's the background for the language, and let me just introduce little pieces here and there as we go. But let me just continue and kind of give you a sense of what you can do with the platform. Most of this doesn't have to do with the language itself. You can use Verilog in the platform. TL Verilog is an extension to Verilog. And so we can code Verilog in here. If I, to that statement, let me just open up the Verilog starting template. So if we want to code a counter, for example, in Makerchip, and just starting with Verilog, since Verilog is familiar, right? So let's do a counter. So we need a count, and I'm sure all of you are much more familiar with Verilog syntax than I am, because I don't use it anymore. Always FF at pos edge clock, and then we can do count gets if reset, it'll get a 0, otherwise it'll get count plus 1. Compile. All right, somebody can tell me what syntax I got wrong here.
Hi, Steve. I think you are going with system Verilog syntax. Logic and always flip-flop, always com, they are system Verilog.
Yeah, that's true. This is compiled with system Verilog support.
Okay.
So actually, there was nothing wrong with it. I was mistaken. We do have our count, and it does count.
Yeah, the logs are giving a green tick mark.
Yeah, so the green tick mark. Nav TLV and diagram are showing a red X, and that's because these are purely features for TL Verilog. So there's nothing to represent for the Verilog circuit. So jumping over to TL Verilog, because it's a little easier to demonstrate. This is again our starting template, and we can do the same circuit in TL Verilog. So we have a count that's 15 to 0. Do it this way. That on reset becomes 0. Otherwise, we want count plus 1. So we do get a diagram, a very simple one. So you can see how students would be able to jump into this platform, teach them some very simple syntax, and have them code up an example, see the circuit in action, be able to step through and see how the values change as the circuit counts. So a little bit simpler than a counter is just some logic gates, right? So you can have them code up, let's say, an inverter and compile. And they have an inverter. They have the input bar, the output foo, and foo is indeed the inverse of bar. And of course, they can step through it here as well. So you can start out very simple like that. With traditional EDA tools, you might spend, a week just getting the students, getting the software installed, getting all the licenses sorted out, getting platform issues sorted out to get to the point where the students are able to run a simple circuit, teaching the basics of Verilog, teaching the students about test benches so they can drive the stimulus to their circuit. You notice here we didn't do any test bench. We just coded a logic gate. The test bench kind of comes for free in Makerchip, in a quick and dirty test bench. And I find this incredibly valuable even for developing real hardware. You just get random stimulus if your circuit's disconnected. We've got bar that's disconnected, and it just gets a random value, so we can see random behavior in our circuit. So very easy for the students to get going. I didn't show the nav TLV tab yet. There's not a whole lot to look at in this circuit, and maybe I'll go back to something more interesting again. So let me go back to the diagram. Sorry, to the divide. Just telling me I've replaced my code. So nav TLV is representing the same code that you see in the editor. It's just represented in a way that's optimized for debug, so I can interact with this view, correlate signals from the code back to the diagram. I can also go live here, so I can see the live values here in simulation, and again, step the simulation to see how the values change. So that's the Makerchip platform. You can interact with the local file system as long as your browser supports it, which means basically Chrome and Edge. Firefox, for example, does not permit interaction with the local file system, but I can open files and I can save them to the server with either this button here. Go ahead and do it. That gives you a link here that you can reopen your design. So this will save back to the server as you're editing. And I think I've touched on everything. You can also use Makerchip in a mode where it's your debugger, but not your editor. So you can edit your code outside of Makerchip and just use Makerchip for the waveform viewer, for the diagram perhaps. And the one tab that I haven't showed is the Viz tab here. So let me
sorry to interrupt again, Steve.
Yeah, don't be sorry at all.
Yeah, just I was asking if I already have a Verilog project, can I translate that to Makerchip and see the visualization?
So yes and no. Some things you can do, some things you can't. So as we saw before, the diagram is...
as we are very much into Verilog programming, so we have projects ready with Verilog and system Verilog. But is there a way to, so that I can port that project into the platform Makerchip and try to see the visualization much better? Is it?
Yeah, so the things that are possible, like I said, TL Verilog is an extension of Verilog. So any Verilog or system Verilog is also legal TL Verilog. You can absolutely put your Verilog project here and it will compile just fine. The only requirements to run on the platform is that you provide a module interface that the platform is capable of interfacing with. So Makerchip simulation has to be able to drive your circuit. So you need to wrap whatever your circuit is in this top level module interface.
Okay.
So this accepts a clock and a reset. These circuits, you wouldn't do multi-clock domain simulation in Makerchip. So a single global clock, a reset.
That's what. Simple only. I'm not going for series.
Right.
Simple.
And then the platform takes back this passed and failed, so that controls the simulation.
As you told that the visualization, if I can show the visualization to my students, like if I can put a project and make it visualize that easily, like what you are showing. I am not showing for complicated structures, just simple models only.
Yeah, just simple things.
In which there is no CDC concept. I'm not going on SOC level, just a simple block.
Right. Yeah, so the waveform viewer absolutely works with Verilog simulation. The diagram does not. So the diagram is representing your TL Verilog, TL Verilog constructs, TL Verilog circuit. So you won't get this logic diagram specifically.
Okay.
The nav TLV won't do a whole lot for you, but actually no, you get an X for nav TLV. You'll get your logs. The next feature I'm going to show you does work with Verilog, and I think this will be very useful even if you're not ready to transition to TL Verilog. So I'll show that in a second. The other comment I want to make is we're actively working on automating the ability to translate Verilog to TL Verilog. So there's a lot of infrastructure in development that you can leverage to help if you did want to kind of upgrade your curriculum to use transaction level Verilog. But even if you're still you have an existing curriculum with Verilog, you can absolutely use Makerchip and not get the full benefits that you would if you were in TL Verilog, but still get some benefits that you've got an easily accessible cloud platform for development that doesn't have all the overheads involved in other commercial EDA tools. But what I want to show next is the Viz tab, and this one's good. I'll open up the simple ring. Hopefully that's the one I think it is. Yeah. So this circuit is a ring topology. This is literally the TL Verilog for the ring circuit. And this source code also has code in it to express how we want to visualize the ring. And that shows up here in the Viz tab. So I can play the circuit forward and we can watch how this circuit is behaving, passing data around this ring. And we've actually instantiated 2 rings, as you can see. So this is, the most unique thing about the Makerchip platform. and incredibly useful in the classroom. So, obviously just looking at this example, very easy to convey to the students what this circuit is doing as opposed to just looking at code.
Yeah, this data flow thing is a new thing, I guess. It's wonderful.
Viz has been around for a while, but it's also been a while since we initially integrated, with eSim. So I don't remember exactly what the state was at that time.
I see.
And now with AI, things get really exciting with Viz, and we'll get there in a minute. Okay, so yeah, so with Viz, you can visualize anything you like. And see what else we can pull up here. Let's see if I listed anything fun for my notes. So this one's fun to talk about, actually. So this example, the backstory is kind of fun. I did a course for the U.S. Department of Defense, and I refuse to call it the Department of War. Teaching folks Makerchip and digital logic, the audience was very mixed. I mean, we had like project managers who had never heard of Verilog, and other students that had gone through an ECE curriculum. They all went through this course. I was focused on RISC-V CPU design, but intro to digital logic, etc., and just kind of survey of how things work in the industry for designing chips. It was fueled by money from the U.S. CHIPS Act. This is a 2-week course, and the last 3 or 4 days of the course is an open project. The students get to do whatever they want. One of the team of 4 students had some experience with AES encryption. And they said, we want to do an AES encryption circuit. And I said, that sounds like a lot of fun, but that's more than a 3-day project for somebody who's never designed circuits before. And they said, you know what, we want to do it anyway. All right, well, we'll see how it goes. And really bright group of guys. So their experience was with AES encryption in software world, and they wanted to translate that into what they had learned with hardware. So they did. I think they got done with a day to spare. They had their AES encryption algorithm running. In that course, we use tiny tape out, which is something that you guys might want to consider as well. Gives the students an opportunity to actually do real silicon tape outs. That tiny tape out ecosystem has this demo board that you can see here, tiny tape out demo board, which is FPGA based. So this chip in the middle is an FPGA, and this chip behaves exactly as their ASIC would after it's taped out. The limited area of an FPGA versus an ASIC doesn't matter, because the whole idea of tiny tape out is that every project gets a tiny little sliver of the silicon. And so that tiny little sliver of an ASIC fits just fine in a small, cheap FPGA. And that's what they have here. So the students get to design in the class with this actual physical board, and design circuits that they can simulate and virtually design with in Makerchip, and then they can program the actual FPGA and see it behave for real. And so that was the platform that the students were working with, and this team designed an AES encryption circuit. They did not design this visualization. I did this afterwards because I thought it'd be a great showcase. So after the class, I used their circuit and I put together this visualization. This comes from Wikipedia. So if you go to Wikipedia and look up AES encryption, you get this picture. And I overlaid on this picture the animations. And so this is how AES encryption operates. So again, very useful to have the visualization to illustrate a concept. I'm not sure how useful it really is for an encryption algorithm where the nature of it is to be as cryptic as possible. But this is kind kind of leveraging the best that Wikipedia contributors could come up with for illustrating how AES encryption works. And instead of looking at a static picture, you're seeing a diagram in action. So these are some of the uses of Viz, and we'll see more. So let me jump over at this point to VS Code Makerchip extension. So here I am in VS Code, and I played around with prompts last night at 11 o'clock and tested this one out, which worked well. So we'll give it a shot again. So this is VS Code with Makerchip integrated in, and we'll just watch it do what it does. But in this environment, you can certainly use this for production design, but since this talk is focused on education, there's a lot of educational value in integrating Makerchip with VS Code so that the students have access to an entire platform. They have access to GitHub, for example, within VS Code. They have access to whatever installed local tools they have. So if they have FPGA, compilation tools and whatnot in this environment, they have direct access. They also have access to AI. So the Makerchip platform itself does not incorporate any AI. We can leverage here the GitHub Copilot. So that's what I'm using. I'm prompting GitHub Copilot here. Help me understand the behavior of a FIFO. Code up the FIFO in Verilog. Wrap it as a TL Verilog file just so it opens comfortably in Makerchip, and use Viz to show me, illustrate what a FIFO is doing. And as I said, the VS Code Makerchip mode is under development. It has some limitations at the moment. This parenthetical note is just to get around one of those. But let's see what it can do. So I'm going to let that run in the background. Maybe I'll just shrink this way down so I can see it in the corner, and we can watch it while we talk about other things. So while that prompt runs, some thoughts for ways you might leverage some of the existing content that we have for teaching using Makerchip. So this is something that's under development as we speak. I have a number of students that are working with me this summer. One of them is working on, well, several of them are working on course curricula. One student is working on this course in particular. So she's putting together a course to introduce logic design, starting from ground zero. So just an illustration of the way course content can be delivered in a completely asynchronous manner and integrate Makerchip. So this is all using Markdown. She put together this course, and as the students are going through the course and learning about, this is using TL Verilog syntax, so learning about how to express circuits in TL Verilog and what the logic gates are all about, they get to see that in Makerchip as they're going through the course. So we teach them logic gates, and then they can see logic gates. And they can continue on, and here's, looks like I need to approve a command over there. So here's a half adder circuit in TL Verilog. They can explore the circuit and see how the circuit behaves. So it becomes a more interactive experience. And then they get to, after they've learned about logic gates, they get a little problem for themselves. Here's a waveform. What's this circuit doing? See if you can match that behavior. So see if you can code up that logic expression and get your circuit to behave like this circuit. And it looks like at the moment that just provides the solution, but it's under development. And so you can provide these fun little activities. I think she's got another one here that's a little more visual. That's just a mux. It's another matching the waveform. Might be quite a bit later, actually. So decoders, multiplexers. Passed it or not, but I just wanted to get to an example that takes advantage of the visualization. So they're doing a little CPU circuit or ALU circuit. Okay, and then this one is what I was thinking of. So a little pixel art challenge problem. Right, so code up a circuit to drive a display with some pixel art. So you can make these problems fun and engaging. All right. An earlier course integration that I've done that I haven't even deployed yet, actually. You can open up content inside Makerchip, so it's right there. So this is kind of similar to this course the student's working on, but it's delivered right here in Makerchip. So again, it's walking through some basic logic concepts. I think I probably, yeah, I have it open here. So this is the reference solutions for that course. So in this course, the students are designing a RISC-V CPU core. This is what they end up with in the end. So they have a little test program where they can see the instruction memory with all the instructions, and they can step that cycle by cycle, see how the instructions are fetched, how they're decoded, how they interact with the register file and the memory. So lots of fun options for delivering content in a way that's more engaging. And do a bunch of approvals for Copilot here. So while that continues to run, well, actually, my next thing was to do another prompt. So let's see how that goes. And while it's running, are there any questions or comments? Yeah, this particular course originated with a partnership with the Linux Foundation, and it's offered in edX.
Wow.
So that's the version that's currently deployed. And there are, I mean, this Makerchip platform is actually, and TL Verilog are pretty popular in India. I think, yeah, BIT teaches, their students just start with this course. That's their introduction. So let's take a prying eye at what the agent is coming up with here.
Someone else wants to ask something meanwhile? CSIR? Someone from CSIR, Siri?
Yeah, thank you, Steve, and thank you, Sumanta sir. The last one is with edX Linux course. Am I right?
Yeah, this course here is.
And the one which with the ring circuit which you have performed, that is in the examples?
That's in the examples within Makerchip itself. So you can just find that within the examples tab here.
I don't know much about TLV, but I'm learning it with very fun, and also the virtual FPGA circuits which you have demonstrated somewhere.
Mm-hmm.
That is also very nice. We are also getting benefited from India.
Super. That's glad to hear.
Thank you. Thank you. Yeah.
Yeah. So I mean, this is an example of the virtual FPGA lab. There's a virtual FPGA lab project that supports a bunch of other FPGA boards and some peripheral devices. It's a project that we've mainly done through students in Google Summer of Code. So it's a work in progress, but you can certainly leverage that ecosystem for FPGA-based classes to enable this virtual experience where the students are able to do their work outside of the classroom when they don't have access to the lab, and then take their work into the lab and actually touch and feel the hardware. Okay, so you saw the agent here. it finished writing its code. It opened that code in Makerchip. Looks like it compiled successfully, which is impressive.
My question is how we involve automation algorithm for a power or area or speed in Verilog code.
How do you optimize the implementation?
Yeah.
Yeah, so Makerchip, the Makerchip platform supports the front end process, so simulation only. It doesn't currently integrate any of the back end tools like logic synthesis. That's certainly on the to-do list, and certainly you can use Makerchip as your front end simulation environment for debugging. And
Just like
use
clock gating or power gating scaling concepts, if we want to involve in our Verilog code, so how we start the automation algorithm in Verilog? How we write?
right. So logic synthesis is not in Makerchip itself, but you can certainly run Makerchip on a platform that has, say, Synopsys tools installed so that you can do logic synthesis, and just do that outside of Makerchip, right? So
You
there's
can
no...
it in Makerchip and pass it through Yosis also, if possible.
Mhm. Yeah, you can use any tool stack you want to do your backend, but Makerchip itself does not run those tools on its own backend on the server.
Maybe implement any power gating or clock gating concept in Verilog code directly rather than using the any backend or another tool. Only we use Verilog for power gating or clock gating. Then we
Yeah,
optimize our design.
yeah. So I can actually talk about specifically clock gating in TL Verilog because it's way easier to do clock gating in TL Verilog. But you can certainly do Verilog or TL Verilog coding as you wish. You can definitely implement clock gating and simulate it. The point is you're not going to see the Makerchip itself does not run power analysis or any of those backend tools. All right, so the agent here says that it's done. Let's see how it did. So what I asked it to do was generate some visualization of a FIFO. Here's what it came up with. All right, so it came up with, it's doing a fill phase where it's writing into the FIFO, and we can see that. Now it's doing a drain phase. We can see how it drains, right? We asked it to come up with an example that illustrates the behavior of a FIFO. It's a good illustration. And so now it's reading and writing, push pop every cycle, sitting idle. Not bad. So one shot to the AI, and we've got an illustrative example of how a FIFO works. And I expect education to really transform where the educational experience is very customized to the individual by the use of AI. You can use AI in any number of ways. So here we asked it to come up with some visualization to explain a concept. You can ask it to create a course based on, based on your background and what you're interested in learning. So this kind of course that I just showed that a student is developing, the student is using AI heavily, of course, and a student can just get the content that they want, ask the AI to explain something to them, to create a challenge problem. All right, so this was my first demo. Couple others. Let's see. Okay, so the next one, I won't run live. Let's just look at the results. So this was one that I ran last night. So I was thinking about what to prepare. So what's a simple game that's popular in India that you could model in Makerchip? Its answer was snakes and ladders. I said, sure, that sounds great. So it built snakes and ladders. And what it built is here. And I can compile that. Ah, there we go. Refresh bug. So this was one shot to the AI, and it generated snakes and ladders. Don't ask me if all these snakes and ladders are in the right place, but from my recollection of the game as a child, it looks about right. And we can watch the circuit play snakes and ladders. So the point here is that you can make the experience of circuit design fun, right? So we can relate this to games. If we have time, I can show a challenge that I'm running over the summer. It's the second summer that I've run the challenge for students to come up with circuits that play games or interact with an environment to compete against other students. So it's gamifying the whole experience of circuit design, making it a lot more fun. That was definitely one of my key motivations in starting Redwood EDA, is that circuit design fundamentally, it's logic games, it's challenges, it's should be engaging and fun, and the industry has made it very stodgy and uninviting. And so that's part of my mission here, is just to make the experience more fun. So that's one. We can also talk about, let's talk about work 5. So this one I pulled up. Let me start with this page and get back to the compiler. So Warp 5 is a CPU that's built out of TL Verilog. It's really an exploration of some of the cutting edge capabilities of TL Verilog and Makerchip as well. One of the goals of TL Verilog is to be able to design your circuit more flexibly, so that in my experience as a circuit designer, a lot of the effort is not designing a circuit in the first place. It's leveraging an existing circuit in a different environment where the parameters are all different. The power budget is different. The clock is running at a different frequency. The layout is different. And you completely have to rip up your RTL and start from scratch. With TL Verilog, you don't have to rip up your code and start from scratch. So Warp 5 is an exploration of how flexibly we can build circuits. With this configurator, you can come in and choose, what pipeline depth do I want for my circuit? What architectural extensions do I want? RISC-V architectural extensions. Enable multi-core.
Hello, Steve. Sorry to interrupt you. Someone is asking if we can do timing analysis.
So timing analysis is one of those back-end physical implementation flows. So no, I only do the front end. It's just simulation. Clock cycles is as far as we get. But again, you can connect that up to any back-end tool you want. So any timing analysis tool that you have locally, you can use, and still use Makerchip as your front-end simulation tool. You can choose the details of your pipeline and various other things. And then you can build that CPU. So the CPU that I built here.
Yeah, this one is available in examples, this Warp 5.
This is just warp-v.org. So you can go there now and play around with it. So what I set up for this one is a custom program. Actually, before we talk about that, let's just, all right, so I'll go back to cycle 58. So this looks a lot like the the visualization for the course. It's using a lot of the same code. So we see the instructions executing as we did before. Let's just reset and jump over reset. So we see the instructions executing and interacting with the register file and the memory. It's got control and status registers. We can see this cycle level view of what's happening. And we get a waterfall diagram to illustrate all of the hazards in the design. We have a load, for example, and that load takes some time. So we've got some instructions behind it that are squashed. And this visualization kind of illustrates all of those hazard conditions. The RE is a replay, which squashes these instructions, redirects the PC, fetches a different instruction. And we can see all of that. So one thing I wanted to show off, which is not mine, this is somebody else's site called Compiler Explorer at godbolt.org. Godbolt is the guy's last name who created this. It's a really neat site for exploring compilers, shockingly. So you can choose from any language you can think of is available. I've chosen C++. And you write some code, it compiles automatically into assembly language. You can relate that assembly language to your source code. So as I'm mousing over different elements in the assembly code, it's highlighting elements in the C++ source code. So it's a really good way to understand the compilation process, instruction set, architecture, etc. Just like it's got a million different languages, it's got a million different compilers as well. This is probably GCC for RISC-V 32-bit. And so I got the assembly code, and then I just copy that code, and I dropped it into Warp 5 here. So that's the code, and then I want to build that in Makerchip. So when that compiles, here I am with a custom CPU core that I've configured to my liking, running a program that I wrote in a high-level language, and I can see how that, how that program executes. I got a timeout. I guess that means a lot of other folks are experimenting with this at the same time, and the server's a bit bogged down, which is a good indication that you guys are engaged. But I'll let that compile, and if it doesn't time out, in fact, what's already compiled here is the same thing, so we can actually just pretend that compiled. So here's that running CPU. We can see how that actually executes on this hardware. So for students, this is incredibly valuable. It's evolving, but I've started to teach with this, and it really exposes the whole mysterious process of going from a high-level programming language all the way down to a gate-level implementation of that design, and really understanding the trade-offs, the decisions, the process. So I thought that would be good to illustrate for everybody. All right, so I'm slated for an hour. I'm past an hour. I mean, I think the timing here is good. Sumanto, let me find out what you guys want to take over and talk about the integration with eSim.
Yeah. So yeah, thanks, Steve, for the wonderful talk. It was nice to have you again. And this RAP, whatever we have shown, and Goldbolt, this thing I remember using RISC-V toolchain and trying out various things. So
Yeah.
these things are making the experience seamless, kind of. Yeah, that's a wonderful innovation. And yeah, so I would so it's a privilege to have you again and listening to you. I mean, I'm kind of fan of Makerchip right now. So yeah, from the audience, I would like to know if anyone wants to ask anything to Steve. it's definitely an opportunity to hear from him.
It's great. I have used Godbolt to convert my code and see how the compilation goes on, but the visualization thing, that's great. Especially the WOB which you showed, I'm definitely going to try that out. It's very much helpful.
Good.
Yeah,
and
thanks.
I will admit, I'm sure you'll stumble over things when you try to use this. This is very much
The Godbolt link is there in RISC-V International. From there we have checked, but so that's visualization is awesome. Yeah, that's great. Thank you.
Truly wonderful. Yeah.
Thanks.
Also, whatever you have shown, the implementation using AI,
VS Code.
Great.
So I think I missed a couple questions, but
to integrate VS in VS Code, how do we integrate? Means from store we have to purchase the link for Makerchip?
No, it would be all just open source. As I said, this is not publicly released yet. I mean, it is all in a public repository. You can actually run it, but it's it's not deployed as a Makerchip, as a VS Code extension in the VS Code marketplace, right? So VS Code has, why am I not seeing the marketplace icon? Extensions.
So right. How do I get it? And extensions means, okay, if I type from there, not there. So how do I integrate it?
Yeah, so it would be just type Makerchip once it is publicly deployed. I expect that'll happen probably around the end of the summer.
Okay, that would be great. That would be great.
If you want to be an early tester, feel free to reach out to me. It'd be good to get some feedback on it. I can make it accessible. It's just not as easy as just going to the extensions and typing in Makerchip.
Okay. How do I reach out to you?
You can, Sumanto has my email. It's just steve.hoover@redwood.com. If you Google Redwood EDA or Steve Hoover,
from the Redwood website, I can get that. Huh?
Yeah,
sure.
I'm sharing this here in the chat box.
Okay, Sumanto, thank you.
Yeah.
All right. So
I got
let me see what other questions we've got.
Thank you, Sumanto.
There are many questions in the chat box. How exactly did you integrate Makerchip and TLV into VS Code?
Yeah, so VS Code has a very rich ecosystem for designing these extensions. And so it's been a process for me over the past many months to kind of rebundle Makerchip so that it can be used first as a plugin, which is kind of the use model that you see in this course. We can integrate it with other things. So it's easy to plug in. You can run Makerchip in a Jupyter notebook. It's very easy to integrate. That was the first step. Once we had that, it was easy to plug it into an extension for VS Code. But yeah, they've got a very rich ecosystem for developing extensions.
Yeah. Now, are there any courses available on FPGA?
So most of the course content that I have available is based on RISC-V. It's primarily variations of the same theme targeted for different expertise, different durations. So these are all RISC-V based courses. I just went to the Learn courses menu in Makerchip. DC FPGA courses is currently empty. A couple TL Verilog trainings, logic design trainings, but this is all evolving. My focus now is more on training AI so that AI can train people.
So the course that is available in Linux Foundation is the basic course, building a RISC-V score, that is LFD111X, that course.
Sounds right. Yeah,
what you showed, it's that one only, na?
Yes.
Yeah, I will be going through that. I was just checking that, and Sumanto has shared me the GitHub repository also related to that. So I will be going through that. That's very much helpful. The app which you showed, that one also is very helpful. Thank you.
Good. Yeah, I want to say, feel free to reach out to me.
Sure.
all of these capabilities are so actively under development that
Sure.
they change quickly, and they're not all bundled to be easy to just pick up and deploy. But feel free to reach out. Maybe I can help you get off the ground with some of this.
Yeah, if you can integrate some way in which we write the Verilog code and it directly integrates to this TLV, because that's entirely new to many of us. That's
I mean, you can certainly
or the other way around also, means if the code is in TLV and there is a way to get the Verilog snippet out of it, then it will be.
Yeah, so this is TL Verilog. If you go to this little E menu and show Verilog, that's currently the mechanism to at least explore the generated Verilog. You can download it as well. So this is showing, this is my source code. This is the total system Verilog that's generated from it. Obviously, the TLV is much more compact. The way it's structured, you have your source code, you have a translated code that's line for line. So you can see the TL Verilog statements translated directly to Verilog statements. And then you have this separate file that's almost entirely correct by construction.
But it's almost looks like that HLS means the complication, what happens in HLS from C++ to Verilog conversion.
It's not that at all. HLS is completely unreadable.
It gives huge codes. When we use HLS, it gives huge
it's not
codes.
the same thing. If you were to code this example in Verilog, you would come up with something of very similar length to this.
Okay, then I will definitely explore that. Yes.
The code that's generated here very closely matches Intel's recommended coding practice.
I will definitely go through it, because HLS is really horrible for.
Right. Yeah, and that's true of most compiled languages. The output is unreadable. That's a definite differentiator for TL Verilog. The code structure in this translated file, it's the code structure that you started with. The signal names are long. They're long because they're descriptive. They have the pipeline number. They have the scope. They are descriptive names, so they're longer. You have that context in TL Verilog, so the names are not are short.
Sure,
but
this is something to look forward to.
If you're coding Verilog with good practice, your names are very descriptive. So not exactly what you would code by hand, but much more. It's much more feasible to generate your Verilog with TL Verilog and then maintain that code as source if that's what you want to do for whatever reason.
Thanks.
Someone is asking, can I transfer the Verilog code I generate here into standard FPGA development tools?
Yeah, you can. It's a language extension, the TL Verilog. Any TL Verilog constructs just convert to Verilog constructs. That's your Verilog code that goes through your FPGA tools.
Basically,
go ahead.
Basically you can send it. You can write in TL Verilog and then send it to Sandpaper SAS, and it gets converted to Verilog. So yeah, you can use it that way.
Right, and the motivation for the integration is to make this as seamless and incremental as possible for folks to transition from Verilog to TL Verilog. You can have a Verilog file that's 6,000 lines of code, and then 10 lines of that you want to write in TL Verilog. You can do that. So it's not exactly language extensions as you might think of language extensions. It's sort of regional. You say, in this region, I want TL Verilog constructs, but that region can be as small as you want.
Any other questions? Okay, Steve, I guess this is done. Yeah.
Good. Thanks, everyone.
Yeah, thank you, Steve, for being with us, and thanks everyone for being patient and listening to us. Thanks for the wonderful session, Steve. We get to know a lot of things from you.
Thanks, everyone.